Hello everyone, excuse me. Remember from last time that we basically summarized all the basic facts that we proved about Lebesgue measure and Lebesgue about measurable sets. So what I want to do in the next two videos is talk about further, more deeper properties about Lebesgue measure. And in particular, I want to talk about continuity of measure and the Borel-Cantelli lemma in this video. The Borel-Cantelli lemma actually is very useful in probability theory. And if you're curious about that, in the video, not in the playlist, but just on the channel contents, there is a video on introduction to measure theoretic probability. So take a look at that. Talks a lot more about Borel-Cantelli from the perspective of probability theory. Okay, so let's just recall some basic definitions that you probably saw somewhere in some way. Continuity of measure. Okay, so yeah, so if we're given any sets ek, we say really so for us, this is going to be a subset of the real line, each ek, but it really could be anything. We say that this sequence of sets is nested if kind of the obvious thing is true. E1 is possibly larger than E2, it's possibly larger than E3, etc., etc. Okay. So the kind of obvious picture here is something like this here, where this is E1, make E2 a little bigger. So this is E1, the largest one, E2, E3, etc. So they're kind of shrinking sets in some way. I could have made this picture better, but I think you get the idea. So on the other hand, if we kind of have the opposite going on, we say that these sets are ascending if they basically kind of get bigger, possibly. Of course, when I write subset like this, they could be equal. So here, it's like the opposite picture. We have some like E1. We have some possibly larger E2, some possibly larger E3, etc., etc. Okay, so we have enough to state what is usually called continuity of measure, and I'll explain why it's called continuity of measure. So there's two parts. Really, one is the main part. So if we have a sequence of measurable subsets that's ascending, then the measure of the union So AK is measurable, so the union is measurable, so I'm justified in writing M without the star here. Remember, M without the star here is literally M star, outer measure, but restricted to measurable sets. So this is going to be given by the following limit. Okay, and two, we have something similar for nested sets. So if we have a sequence of nested subsets of the real line that are measurable, and we have that the measure of B1 is finite, then the measure of the intersection is going to be the limit of, sorry, there's no AK here, it's just BK. It is going to be the limit of the measure. And again, I'm justified in writing M because the intersection, countable intersection of measurable sets is measurable. All right, so if it's not clear, and it might not be clear, to be honest, book doesn't really, I don't think they really talk about this much. Yeah, so why is this called continuity of measure? Where is continuity here? Okay, so let's look at one here. So I'm assuming that these sets are ascending. So if these sets are ascending, so we're in this kind of situation here. Instead of E's, it's A's. Obviously, we have, here that E3 is the union K equals 1 to 3 of E3, and in general, this is going to be true. So I just write 3 because I have the picture here. E3 is the largest. All of these are contained in E3. So you're not doing anything by taking unions. So in general, based on this here, we have En is the union K equals 1 to N of Ek. Well, N is an integer here. Okay, so yeah, we have nested, we have ascending sets here. So An is going to be this union here. Okay. So I'm going to put this in parentheses because there's really no way to assign meaning in the literal sense to the limit of the ANs. The ANs are sets. There is no such thing as the limit of sets, really. But intuitively, what should this limit be? Well, intuitively, the limit here is just the union. I mean, like, these sets are increasing. They're just getting bigger and bigger and bigger, possibly. Some of them could be equal to each other, but in general, they're getting bigger and bigger and bigger. So, the limit, in some sense, is just like the totality of all these sets, which is just kind of the whole union, or in some sense here, if you want to like let n go to infinity, quote unquote, you're going to get the union. Again, that's completely not rigorous, but I'm just saying intuitively, it's reasonable to think of this limit here right here as the union. Okay. And so what continuity of measure is saying, I'll do this here. Continuity of measure is saying that because the AKs are ascending, this is going to be this limit here. So that's the intuitive idea. Now I want to emphasize, do not write something like this on the prelim. I guarantee you the grader, even if it's not me, might very well be me, but if it's not me, the grader will be pretty harsh because this is devoid of literal meaning. It has the intuitive meaning, as I mentioned, this set here has the intuitive meaning, only particularly when the sets are ascending. It has this, this kind of intuitive meaning as the limit, but really it doesn't have meaning. But anyway, so intuitively we can pull limits out of measure, and a similar thing is true for intersections and nested sets. Okay, so right, so let's prove continuity of, well, actually, I want to make another note before I do that. Sorry about that. And that is, this is just not true necessarily without this condition. It just isn't. And it's very easy to give examples. So let's say bk is something for any integer k as simple as k to infinity for any positive integer k. Okay, so let's compute this intersection here. Well, there is no real number in there is no number whatsoever in all of these sets. So this is empty. All right, so that means this intersection here is 0, whereas this limit here is infinity, because each one of these has infinite measure. I mean, this is an infinite interval, so there's really no ambiguity here. So you really don't get any worse failure than this. It's infinity is not equal to 0. And again, what I want to stress here is that M1 is infinite. M of B1 So without the condition that I wrote before, that the measure of B1 is, without the condition that it's finite, continuity of measure for nested measurable sets can miserably fail. All right, so I need one proposition, which is very, very easy to prove, but it's so useful that we give it a name. It's called the excision property. Excision meaning, you can excise something from something else. You can kind of cut something. I think I'm spelling that right, but anyway. So what is this? So if I have a measurable set with finite measure, and I have anything, in fact, usually this is stated for two measurable sets, but there's no need for that really. If I have anything larger than E, then the measure of A take away E is, or the outer measure is the outer measure of A minus the outer measure of E. And I'm using outer measure because A need not be measurable, and hence A take away E need not be measurable. I mean, this one here really is the measure of E, because I'm assuming E is measurable. But generally speaking, if you're dealing with sets, some of them are measurable, some of them are not. It's just better to just write outer measure so as to not confuse anybody. I mean, I won't take off if you do write like m star of A take away E equals m star of A minus m of E, because that's technically true. But if you do write m, if you wrote m's everywhere, that's not true, and I would take off because it's not a minor sin. I mean it's not a big deal, but I do want everyone to understand the difference between measurable and non-measurable sets. So for example here, I guess I could write outer measure, but whatever. Anyway, so yeah, so here the picture is fairly clear. So I have this bigger E here and this little A here. Okay, so what's the proof? Proof is really just use measurability. So E is measurable. So we know literally by the definition, nothing more than that, that the outer measure of A is the outer measure of A intersect E, A intersect E complement. Well, A intersect E is A. A is, sorry, I have these mixed up here. I don't know why I did that. A is a larger set, and E is the smaller set. So A intersect E is fairly obviously E because A is larger than E. A contains E. So this is going to be the measure of E, and this is the outer measure. And this is the outer measure of A take away E. So this is true no matter what, no matter whether the measure of E is finite or not. As long as E is measurable, what I have in the blue is going to be true. Now, if the measure of E is infinite, we really can't subtract the measure of E from both sides. It's just devoid of meaning necessarily. But if the measure of E is finite, there's no problem here. And I guess I'll write outer measure here. Yeah, the outer measure of E is finite, so I can subtract both sides. Sorry, the outer measure of A minus the outer measure of E is the outer measure of A take away E. And that proves it. So not a whole lot to this little proposition. Yeah, so just to emphasize the point I was trying to make, it really doesn't this doesn't really make sense if the outer measure of E is infinite. So I'll do two examples here. Let's say E is, let's say E is 0 to infinity. There's a million examples you can use. And let's say A is R. So A take away R is going to just be, A take away E is just going to be minus infinity to 0. So the outer measure of A take away E is infinity, whereas M star of A minus M star of E is going to be infinity minus infinity, and that just doesn't, we're kind of in L'Hopital's rule territory. We just don't assign meaning to infinity minus infinity. Okay. Right. And if we did, we would kind of want it to be infinity in this example. On the other hand, we could do something like E is the real line itself. So this would be empty. So this would be 0. This would still be infinity, infinity. So if we assign meaning to infinity minus infinity, we would kind of want it to be 0. So this just doesn't really make sense if the measure of E is infinite. All right, enough of that. Okay, so let's get to the proof of 1. And I'll just remind you of what 1 is. We're proving this here. The A's are ascending. The measure of the union is the limit of the measure. Okay, so we're going to put the disjointification to another good use. So first, there's two cases. The first case is that all the AKs have finite measure. Okay, so in this case, just remind you of this disjointification process. Let's say A1 prime is A1, and AK prime is AK take away A, K minus 1, for K bigger or equal to 2. Okay. So the homework that I assigned, that I don't remember when it's due, but I think it's due soon. Sorry about that. So by homework, I just want to emphasize that these are measurable because the AKs are measurable. Obviously, this is measurable also. A1 is measurable. So I really like this proof because it really combines a lot of the things, a lot of the basic properties that we've talked about. So the AK primes are pairwise disjoint, and hence I'm writing the square bracket here versus just the regular union kind of U, because we don't know if the AKs are necessarily pairwise disjoint or not. Okay. Right. So let's use this fact here. Right. Then that means the measure of the union is, well, the two sets are equal, so not a whole lot to this. It's the measure of this disjoint union of the AK primes. And this is going to be equal to, because these are pairwise disjoint and measurable, this is the measure of the AK primes. Okay. So what I want to do is, well, I'll just rewrite it. So I want to write this as m of the measure of A1 prime plus k equals 2 to infinity of the measure of AK prime, because we know what this is going to be equal to. By definition, A1 prime is A1. That's how we define it. By definition, this is a k take away a k minus 1, but the measure of each of these sets, ak minus 1s for any k, is finite. So I can use the excision property, and I can write this as the measure of ak minus the measure of ak minus 1. We cannot do this unless each of these has finite measure, but we're assuming each of these has finite measure. And again, this is from the excision property that I just proved a moment ago. Okay, so right, so this is going to be equal to m of A1 plus this sum here, m of AK minus m, measure rather, AK minus 1. Okay, so right, so this is going to be, by definition, it's the limit as k, well, m of A1 plus k equals 2 to the n. Take the limit of that as n goes to infinity. It's the limit of the partial sums. So yeah, you can write this out. I'll just write out a few of these. So when k equals 2, this is going to be A2 minus A1. Right, so I'll do one more. MA3 minus MA2. This is K equals 3. Okay, but you can see that everything cancels out, except you're left with basically, if you go from k equals 2 to n for an integer n, you're literally left with the measure of an. So by definition, this is equal to, when I say definition, I mean the definition of an infinite sum, literally the definition of an infinite sum. This is a measure of the limit of an. Okay, so that proves it in the case of the measure of each of these AKs being finite. If that's not true, well, we can still prove this fairly easily. Okay, so sorry, that. So if the measure of for some integer k0, this is infinity. Then, yeah, so if this is true for some integer k0, whatever it is, well, then just use basic properties of outer measure that we've proven, or measure, same thing, for dealing with measurable sets. So obviously, AK0 is a subset of the union. I mean, that's a really neat explanation here. It's just, yeah. Each one of these is a subset of the union. So by the monotonicity property, this is the measure of the union is infinity. So we just need to prove that the limit of the measure is also infinity. And that's pretty easy by definition, because because these are ascending, AK is larger possibly than AK0 for K bigger than K0. So that means, yeah, it means infinity is bigger or equal to measure of AK if K is bigger than K0. So that means the measure is infinity. Okay. So again, the punchline here is that both of these are infinity. Infinity equals infinity. That's fine. The measure of the union is infinity. And the limit of the measure is also infinity. All right, so let's prove 2, that if we have nested, if we have nested measurable sets, and the measure of the largest one, the first one, is finite, then the measure of the intersection is the limit of the measure. Okay. So we kind of, so it's a little bit of a trick using basic set theory. So we want to convert intersections to unions. We kind of have to take complements to do that. So let's say dk, let's define dk to be b1 minus, take away bk. So unambiguously, d1 is the empty set. Okay. In case there's any doubts or confusion, d1 is the empty set. Okay, so these are ascending measurable sets. Each of the b's are measurable, so these are measurable. Because the b's are nested, these are going to be ascending. So, right, let's use what we proved a moment ago. So the measure of the union is the limit of the measure okay, and this here is going to be, well, right, so this is going to be the measure of b1 take away bk. This is going to be 1 second. Yeah, sorry about that. Right, so we know that BK is a subset of B1, and the measure of B1 is finite. So the measure of each BK is also finite. So by the excision property, we know that this is going to be the measure of B1 minus the measure of BK. Again, this is by the excision property because BK is a subset of B1. And the measure of B1 is finite, so by monotonicity of big measure of BK is finite, so I can use the excision property, right? Okay, so yeah, sorry about that little waste of time there. Had a little brain fart for a moment there. Okay, so this is going to be equal to the measure of B1 minus the limit of the measure. Okay, so we just want to, basically what we want to do here is basically get the measure of the intersection somehow. So how do we do that? Well, that's not too bad. So dk by definition is B1 take away BK. And this is going to be, I believe this is De Morgan's law. This is actually going to be B1 take away the intersection of the BKs. So we can use the excision property one more time. Okay. And in particular, the measure of B1 minus the measure of the intersection is going to be equal to the measure of B1 take away the intersection it's a little messy, so let me clean that up a bit. Okay, and right, so this is going to be the measure of the union. And we basically, yeah, we basically just figured out what that is. That's going to be this limit here, or this minus the limit. Okay, so using this here, this is going to be equal to the measure of B1 minus this limit here. And now we're basically done. What do we have right here? We have the measure of B1 minus this limit. What do we have here? The measure of B1 minus the intersection. Well, I can subtract the measure of B1 from both sides because the measure of B1 is finite. There's no problem whatsoever subtracting the measure of B1 from both sides if it's finite. We would have a problem if it wasn't. And as we've seen, if the measure of B1 is not finite, this line of argument can miserably fail. So yeah, you just subtract the measure of B1 from both sides here, and then just minus both sides. And then we get exactly what we wanted. The measure of the intersection is going to be the limit of the measure. Okay, and that proves it. Okay, so right. So what I want to finish up with is something called the Borel-Cantelli, which is in some sense a version of this, I guess, for arbitrary measurable sets. Yeah, this is actually very closely. So we're going to use this later in the course, particularly when we talk about Egorow's theorem. I think you might need it for Lucin's theorem. It's just overall very useful, extremely useful result. So we need a definition that's very, very useful that you'll use throughout the rest of the course, literally throughout the rest of the course. And that's the concept and definition of almost everywhere. So a definition so a property holds almost holds for almost every x in E, where E, let's say, is measurable. And I put this in quotation marks because I'm kind of defining what this means. If the measure of x in E, where the property fails at x, equals 0. Okay, so really you kind of want to think in terms of probability in some sense. We're kind of saying, like, theoretically the set here might not be empty, but it's small in the sense that it has 0 size, or if you think in terms of probability, it has like no probability of happening. Or, there's 100% chance of the probability occurring. And again, if you want more of a probabilistic kind of feel for this, just go to that video I mentioned that I made, Introduction to Measure Theoretic Probability. Okay, right. So yeah, we'll do examples of almost everywhere throughout the course. So for now, I just want to prove the following. And this actually itself was a prelim problem, June 2017, number 1. And there's there's at least two kind of versions of Borel-Cantelli. One of them is much more probabilistic and kind of feel. And for that, you can go to the video I mentioned a minute ago. Right. So let's say we have measurable sets EK with the sum of the measures being finite. So then almost every x belongs to, at most, finitely many of the EKs. So that. In other words, the set of all x and r where x belongs to infinitely many of the EKs, that set has 0 measure. That's the definition of saying for almost every x and r, x belongs to at most finitely many of the EKs. We're saying this property holds for almost every x in R. Okay. All right. All right, I'm running out of room here, so I'm going to start erasing stuff. Actually, maybe I'll just erase stuff. So I'll go one more and then start erasing in a moment. Actually, no, I don't want to do that. So let me start erasing here. Just give me a moment. Sorry about this. It's really annoying that you only have 20 slides here, but luckily erasing is not too bad for Zoom. So let me erase this here. Yeah, so what I want to do right now before I prove it, because the proof is actually very straightforward, I want to kind of rewrite what it means to belong to infinitely many of the sets. And this is an extremely important skill to do in probability theory, writing very practical events in terms of intersections and unions. Okay? So in terms of kind of probabilistic thinking, this is kind of saying, you're kind of measuring the likelihood of infinitely many of the EKs occurring, and this is saying that has 0 probability. There's 0 probability that infinitely many of the EKs are going to occur. Okay, so, right, so okay, so I'm running out of time, so I think I'll do this maybe in office hours as a good kind of exercise. So the set of all x such that x belongs to infinitely many of the EKs is going to be the intersection of the union, and this really should kind of make intuitive sense. If x belongs to infinitely many of the EKs, and no matter what n is, x is going to belong to this union. There is some EK for k larger than n where x is in that EK. And I don't care how big n is. It could be 100 million, trillion, gazillion, raised to the 100 million, trillion, gazillion. If x belongs to infinitely many of the EKs, there is an EK larger than that gigantic number that I just stated, where x is in EK. On the other hand, if X is in every single one of these unions, then X is in particularly infinitely many of the EKs. Otherwise, X would not be in X would not be in every single one of these intersections. There would be an N where X is not in EK for any K bigger or equal to N. So I basically told you even how to prove that these two are equal, but still important to actually write this down carefully. But that's the key to proving Borel-Cantelli. So, right, proof of Borel-Cantelli. Okay, so the proof is as follows. So, let's, I don't know, let's call this set here A, for lack of anything better to call it. Let's call this union here D. Let's call it, I guess, DN. Or maybe, I don't know, I'll call it AN. It doesn't really matter. Okay, so our task, as I mentioned, by definition, is to prove that the measure of A is 0. The measure of all X that belongs to infinitely many of the EKs is 0, which is exactly saying that the measure of the set where X belongs to infinitely many of the sets, or sorry, yeah, it's exactly the same. Sorry, it's exactly the same thing as saying for almost every X in R, X belongs to at most finitely many of the sets EK. By definition, that means the set where that's false has measure 0. The set where that's false is exactly A. Okay. Sorry, I had again a little tiny brain fart there. Okay, so yeah, so you just have to notice that yeah, you just have to notice that that AN here is a set of it's a set of nested it's a sequence of nested sets. Certainly this is going to be shrinking as n gets larger and larger because you're taking the union of less and less sets. Okay. So this is a nested right. So because 1 second, sorry about that. Right, sorry about that. So we have that the measure of A is the measure of the intersection of dn, and that is going to be the limit of the measure of dn. Now you want to be careful. This is not true unless the measure of d1 is finite. Well, let's check that. D1 is the entire union. So by countable subadditivity, this is going to be the sum of the measures, and that's finite. That's our assumption, that the sum here is finite. And again, this is by countable subadditivity. So we're allowed to use continuity of measure because a measure of D1 is finite and these are nested. So maybe I'll, just to make sure we're all on the same page here. By definition, again, this is the union k equals 1 to infinity. K, countable subadditivity. This is finite. Okay, so yeah, let's finish this up real quick. So this is going to be the measure of this union here. Basically, it's almost the same thing as this to finish up the proof. K equals n to infinity. EK, sorry about that. So now I just want to use countable subadditivity one more time. Limit doesn't go anywhere, but this here is going to be k equals n to infinity of the measure of EK. And you should know what this is going to be equal to. Because this sum here is finite, this is going to be 0. Because this is finite, the limit of the partial sums, or rather the limit as k, this is kind of the tail end of the sum, and the limit of the tail end of the sum as n goes to infinity is going to be 0. Okay, so we're done. The measure of A is less than or equal to 0. Okay. And again, that's exactly what we needed to prove. The measure of A is 0, which is the same thing as saying the measure where the property that almost every x belongs to at most finitely, the measure where almost every x belongs to at most finitely many of the EKs is false. That has measure 0, because the set where that is false is A. All right, so next time we're going to talk about another extremely useful property that is very useful, particularly if you do measure on very abstract metric spaces, topological spaces, and that's outer and inner regularity of Lebesgue measure. All right, so long, take care, till next time.